I'm Eric Neyman, and this is joint work with George Noarov and Matt Weinberg. I'll start by telling you our question and why you should care about it. I'll give you a motivating example. So around the year 2000, weather models got a lot better. In the 1990s, the way that weather models generally worked was that a model would make its best guess at the initial conditions and then extrapolate from there. But this didn't work very well because we don't know the initial conditions very precisely. By contrast, the way that modern weather models work is that they run multiple simulations based on randomly sampled initial conditions. And our question, phrased in the context of weather modeling, is how can we incentivize a weather forecaster to run many simulations so as to give us a precise forecast? So let's think about this from the perspective of someone who wants to elicit a forecast. So let's say that you want to know the probability that it will rain 5 days from now. The way that you incentivize a forecaster to give you a truthful forecast is by using a proper scoring rule. And for our purposes, a scoring rule is a function S where a forecaster receives reward S of the probability that they assign to the event that eventually happens. So to unpack that a bit, if a forecaster reports a probability X of rain, then they will receive reward S of X if it rains and S of 1 minus X if it doesn't. And a scoring rule is called proper if a forecaster maximizes their expected reward by reporting their probability honestly. And here I have the formulas for the quadratic and logarithmic scoring rules, which are the two most commonly used proper scoring rules. Now, we will really care about this function R of X, which is the expected reward of a truthful forecaster with belief X. And the reason that we care about this function R of X, I've written down here, is that we care about how a rational forecaster behaves, and a rational forecaster wants to maximize their expected reward. Now, remember that our goal is to find a proper scoring rule that incentivizes a forecaster to give a precise answer. So let me formalize this by telling you our model. So there is some true probability P of rain, which is drawn uniformly from 0, 1, and is unknown. But the forecaster has access to a coin that comes up heads with probability P. The forecaster can flip the coin as many times as they want, but at a cost of C per flip. So if you're thinking about this in terms of weather modeling, you can think of a coin flip as analogous to running an additional simulation of the model, and C as the cost of the compute required to run the simulation. When the forecaster is finished, they report their probability, and they're rewarded with a proper scoring rule S that you tell them in advance. Now, the forecaster gets to choose how many times to flip the coin adaptively. And I just want to point out that the question of which probability the forecaster should report is easy. Right, they're incentivized with a proper scoring rule, which means that they should say what they believe. But the challenge for the forecaster is figuring out how many times to flip the coin. And that is what we will spend most of our time reasoning about. So let me elaborate a bit on the question that we want to ask. So remember, we want to ask which scoring rule is best at incentivizing precision. And what I mean by precision here is that we want to minimize the forecaster's expected squared error. So the expected value of the squared difference between the true probability P and the expert's report, which we will denote with Q. Now, as currently stated, this question of which scoring rule is best is kind of silly, right? Because you can take any proper scoring rule, multiply it by 1 trillion, and suddenly the forecaster has really powerful incentives to be precise. Now, of course, you can only do this if you're willing to pay the forecaster $1 trillion. So to make this question interesting and relevant, we will be comparing normalized proper scoring rules. So we will normalize a scoring rule by insisting that an uninformed forecaster gets reward 0, and the expected reward of a perfect forecaster will be 1. And so now we can rephrase our question as, which normalized proper scoring rule is best at incentivizing precision? And specifically, our work focuses on the limiting case where the cost C per flip approaches 0. So to get a handle on how the forecaster behaves, we first need to understand the probability that the expert thinks at any given time. So let's say that the forecaster has seen H heads out of N flips. What is their estimate of the true probability P? The answer turns out to be H plus 1 over N plus 2. And as a sanity check, you can plug in H equals N equals 0. So this is the case before the forecaster has flipped the coin any number of times. And then you get 1/2, which checks out, because remember that the prior P, remember that the true probability P is drawn uniformly from 0, 1. And so the expert's prior is in fact 1/2. Now, I want to guide you through an example of how the forecaster might reason about what to report. So let's say that the cost per flip is 2 cents, and the scoring rule that we are rewarding the expert with is the quadratic scoring rule, in which case the expected reward function of the forecaster is R of X equals 1 minus X times 1 minus X. The forecaster starts out with a guess of 1/2. And so their expected reward is R of 1/2, which is 0.75. So now the forecaster goes through the following reason. They think, okay, with probability 1/2, I'm going to flip heads and update to 2/3. And with probability 1/2, I will flip tails and update to 1/3. So what this means is that after flipping the coin, their expected reward is 1/2 R of 1/3 plus 1/2 R of 2/3, which is 0.778, which means that the expected increase in reward after flipping the coin is more than 2 cents, which means that it is worth it for the expert to flip the coin. All right, so say that the expert flips the coin and say that it comes up tails, so their new guess is 1/3. Now the forecaster can go through the same reasoning, and if they do that, they will find that flipping the coin again only increases their expectation by 1.4 cents. This means that it is not worth it for the expert to flip the coin again. And so the expert will stop there and output 1/3. I'll note that on the previous slide, I was thinking about a locally adaptive forecaster or a myopic forecaster who basically decides whether to flip a coin based on whether it is immediately worth it. You could imagine a globally adaptive forecaster who might sometimes choose to flip a coin even if it's not immediately worth it, to preserve the optionality of flipping it again in the future. All of our results hold for both locally and globally adaptive forecasters. So now I want to tell you the main ideas behind our main results. And to give you a sense of where we are going, here is an informal statement of one of our main theorems. So the statement is that we came up with a formula, which we called the incentivization index, which captured how good a proper scoring rule is at incentivizing precise forecasts. And you can see so the lower this number is, the better a scoring rule is at incentivizing precision. And what this means is that we can compare scoring rules head to head by comparing their values. So in the next few slides, I am going to give you intuition for how we came up with this formula. And this will be exactly that. It will be intuition, not a formal proof. So let's think about the reasoning that we went through on a few slides ago, but in more generality. So let's say that the expert has seen H heads out of N flips. So their current probability is H plus 1 over N plus 2. And so their expected reward right now is R of H plus 1 over N plus 2. Now they can go through the reasoning, okay, with probability H plus 1 over N plus 2, they will flip heads and update to H plus 2 over N plus 3. Otherwise, they'll flip tails and update to h plus 1 over n plus 3. And so they can reason about their expected, which is this green number here. And if you think about it, for large values of n, you can approximate this green value really well by this quantity right here, r double prime of z times 1 minus z over 2n squared, where z is just our convenient notation for the forecaster's current belief of h plus 1 over n plus 2. So what this means is that, approximately speaking, the forecaster flips the coin so long as this quantity, their expected reward, is at least c. Sorry, their expected increase in reward from flipping the coin is at least c. Now, we can rearrange this inequality to find that the forecaster flips the coin so long as the number of flips n so far is less than or equal to this radical. Now, since we are considering the limiting case where c is small, once the forecaster is even considering giving up, their belief z is already very close to the true probability p, which means that we can essentially approximate z with p and find that for any given p, almost surely the forecaster flips the coin roughly this many times. Now, this is good news, because if we know how many times the forecaster flips the coin, then we have a great sense of the distribution of the forecaster's final estimate Q that they report. Specifically, roughly speaking, it is distributed according to a binomial distribution with centered at p, with sample size equal to the number of times that they flip the coin. And since we care about the forecaster's expected squared error, well, that is equal to the variance of this distribution, which is precisely this red quantity over here. And in general, if you care about the expected ELF power error of the expert's error, then that is equal to the ELF moment of this distribution, which is this value in red right here. So let's run with this generalization and think about this expected ELF power error. Now, remember that in our model, p is chosen uniformly from 0, 1. Which means that the forecaster's overall expected error is equal to the integral from 0 to 1 of this expression. So that is equal to the integral of, so this integral right here in red, times some constant that depends on c and l. And we call this integral the incentivization index, the ELF power incentivization index of the scoring rule S. So the lower the incentivization index, the better, because the incentivization index captures how far the expert is from the right answer in expectation. So this has been informal, but to put the main result up on the slide, basically our theorem is that the incentivization index accurately captures the forecaster's expected error. So specifically, the limit as the cost c approaches 0 of c to the negative l over 4 times the expert's expected ELF power error is a constant multiple of the ELF power incentivization index. Now, this is pretty cool because it means that we can compare any two scoring rules head to head by computing their incentivization indices. And whichever scoring rule has a lower incentivization index, that scoring rule is better in the limit as c approaches 0. Now, in fact, we ran some simulations and found that for small but realistic values of c, the incentivization index really does capture which scoring rule is better. Basically, the takeaway, I think, is that you can realistically use our incentivization index to figure out what scoring rule to use for your problem. Now, armed with this tool, we might ask, okay, which of the log scoring rule or the quadratic scoring rule is better? And it turns out that for values of L, such as 1 and 2, the log scoring rule is better than the quadratic scoring rule. And it turns out that there's a somewhat less often used scoring rule called HS, which beats even the log scoring rule. So that's pretty interesting. And the question that I promised an answer to is which scoring rule is best at incentivizing precision? So we can formally ask, what is the normalized proper scoring rule that minimizes the ELF power incentivization index? This is a continuous mathematical program, and we can solve it. And this is the expression that we get. Now, this isn't the nicest expression I've ever seen, but to me, it's remarkable that this question even has a closed form answer at all. So I'm not trying to convince you that this scoring rule is what you should use for your application, but this opens up some interesting questions that you might ask, such as which scoring, how close are the quadratic and logarithmic scoring rules to the optimal scoring rule? Or what do these optimal scoring rules even look like? And the reason that these questions are interesting in the first place is because we proved a theorem which says that the incentivization index accurately captures how good a proper scoring rule is at incentivizing precision. So now let me show you what these scoring rules look like. So right here, I have a GIF of the optimal scoring rules in orange for different values of L compared to the log scoring rule in blue. So here's L equals 1, 2, 4, 8, 16. And this is the limiting case as L approaches infinity. Now, you might be more used to thinking about the scoring rules in terms of their expected reward function. So this is basically the same plot, except for R instead of S. Now, you might also be wondering how good are different scoring rules for different values of L. And so I want to focus your attention on the top 4 lines of this table. So what we find is that the aforementioned HS scoring rule is really close to optimal for values of L such as 1 and 2. So absolute error or squared error. Then if you increase L a bit, the log scoring rule starts being very close to optimal. And then if you increase it more, the quadratic scoring rule becomes really close to optimal. And finally, as you increase L and those 3 scoring rules start getting worse, the spherical scoring rule starts getting really good. So this shows some sort of intuitive trade-off between how good scoring rules can be at different values of L. To summarize, we set up a model for information gathering in terms of flipping coins at a cost and asked how a strategic expert behaves in this setting. We calculated the forecaster's expected error in this model, and this gave us an incentivization index, which captured the effectiveness of a proper scoring rule at incentivizing precision. Finally, we determined what the optimal scoring rules are according to this index. I look to be out of time, so I will stop here, but I am happy to take questions about these future directions or anything else that I've talked about. Thanks.